on these topics. So he's going to tell us about some beginning of the discussion, some series of questions. Please, Thomas, go ahead.
All right, thank you. Given that everybody's probably hungry, there's not so much time. I should really try to go as quick as possible because the idea is to have a discussion. Right, so the original goal of string theory was beyond achieving internal consistency, like understanding black hole microstates, but to say something about the observations, cosmology, particle physics, what we just heard about, and today we also often hear about black hole astrophysical observations. So personally, I think internal consistency by itself is deeply constraining and makes enough arguments to work on string theory. But I want to ask to the audience, have we given up on making predictions at reachable energy scales? We have always known, since the very beginning, that the principle of decoupling in science, in physics in particular, is an obstacle, all right, to do this. And the question is to the audience, how much is decoupling an obstacle? And this is a fact which is not at all related to string theory. All the criticism on string theory, in the end, you can track that criticism down to the issue of decoupling, all right? But then we should keep in mind that not everything is an issue of energy scales. Axion physics is an example of a low energy imprint of high energy physics, or I don't know, dipole moments or something like that. So I want to reflect on something. Wait, how can I go back? Underneath? Good, I'm doing it correctly. So I want to reflect on what we have been doing in string phenomenology in the last 20 years, and I want to do that using a tweet from one of our esteemed colleagues here. And the tweet says, let me read the last sentence. In short, string phenomenology has not been very successful, to put it mildly, and further exploring that route does not seem very useful to me. I think it's totally fine to say this, especially in the context of this kind of social media. I do not oppose this. But I want to say that I think we have learned tons by practicing string pheno. We have learned about geometry. We have learned how field theories geometrize. We have understood patterns in field theories, in effective field theories, weak gravity. We have gotten ideas for new field theories like dBi inflation. We understood deep-brain physics much better. Why or how did that happen? Because phenomenology triggers questions that you might not think about otherwise. And I want to give one example, which is a formal question in ADS CFT. I take a CFT and ask myself, how many bulk dimensions does it emerge? Does it predict? In particular, how many compact ones? And how small can these compact dimensions be with respect to the ADS scale? This is important in phenomenology because we don't see any extra dimensions so far. Right? So it translates into a very cool CFT question, which we don't have the answer for. A third reflection is you cannot deny what has happened with the Swampland program and the impact on phenomenology, on string phenomenology. And so maybe I want to relate this to the following simple question. Maybe this is too simple, but if we want to describe the real world, have we been working in the right direction? So the way I perceive string phenomenology as done before the Swampland sort of took off is that we were asking ourselves how a certain effective field theory can be obtained from string theory. This is not the way science normally works. You go the other way, right? So asking how can we get the standard model from string theory, is that the right question? I think, this is my interpretation, a little bit of a good thing of the Swampland program is that we rather ask directly, how should our universe look like? I think it's a different question. So it's more about focusing on patterns, bounds, and asking the reason why we see these patterns, why we see these bounds. Okay? And to do this, we need to use a paradigm. And I also want to ask to the audience, are we using the right paradigm? So what is a paradigm? Usually it's a critical superstring, or M theory. So we have 6 compact dimensions that we call them to be small. And I want to ask, really, is there not more? Should we maybe think more about brane worlds as we used to do, where M6 is less fine-tuned, because that's where a lot of our problems hide? Think of the dark dimension scenario. dark bubbles. Maybe there is much more. And I'm asking, are we sufficiently thinking outside of the box? Also, another thing which is surprising is that there's so much focus on constructing the landscape, on constructing vacua, and understanding the fluctuations around it. You seldom hear people pondering about how does one dynamically reach a certain vacuum. Okay? For instance, we see in constructing vacua, we already can see that you cannot, in string theory, decouple cosmology from particle physics. This is, for us, string theory is completely natural. People outside of string theory don't even see why that would be the case. And I think this is a super healthy aspect of string theory, and we should take it more serious. And I want to ask, have we sufficiently coupled early universe cosmology to particle physics? And I'm talking specifically about the dynamics that I mentioned before. Do we need a theory of initial conditions to do that? Is quantum cosmology such a theory, or is it a little bit too naive? Maybe inflation is just a dream of using four-dimensional effective field theory to describe the early universe, right? Perhaps the dynamics of the early universe was the dynamics that caused the universe to become 4D, and then it's not 4D physics, right? So, last thing about the paradigm, many things that we do in string phenomenology are well understood in an asymptotic regime. We heard that today before. So some kind of an effective weak coupling in the right duality frame. For instance, the absence of de Sitter critical points, I would say, is pretty much established in this regime. So it's clear to us that a lack of formal string theory progress, maybe we need a new revolution, is actually hampering us. Okay? So it's clear that formal string theory development will be very good for phenomenology. Yet you could still ask yourself, could we be lucky? Is our own universe weakly coupled? Maybe the smallness of the CC is telling us this. And this is an old question which goes back to 85. And I'm also asking the audience, I mean, what our stance on this, you know? So the questions for debate could be the following. You can completely ignore them. I'm just trying to, you know, say something, but it's up to you here in the audience. So the question one, how much is decoupling an obstacle? Should we have focused more, or should we focus more on patterns of effective field theories that you get from UV completion instead of always just focusing on how to get a certain effective field theory? Could our universe be weakly coupled in a string theory sense? If so, we are lucky. We can do the computations. Is the critical superstring with small compact dimensions the right paradigm to use? Can we decouple cosmology from particle physics, as we probably too often do? And which is our best or worst target for observing string theory? We heard about particle colliders. We heard about cosmology. As I mentioned, there's black hole phenomenology, black hole observations, which have not been mentioned. These are my questions for the audience. Yeah.
Thank you, Thomas. Perhaps with these questions, we can bring in the previous speakers, because these are general questions that we can. So the previous speakers, Michelangelo, and Marco, yes, please come forward. I guess there's the microphone you can, all three of you can wear, so you can. Okay, and then I will sit down and let you take care.
So there can be questions for the two other speakers, questions you were not able to ask, and any question about string phenomenology. There's no reason to stick to what's here on the slide. Miguel?
So I have a question, perhaps it's more for Marco. So in Shusa's talk, we heard about, the hints from Desi, like looks like there might be hints of, time variation in cosmological constant. How excited do you think we should be about this? How excited are you?
I'm exactly, I don't know, 3 sigma excited. So which means that we have seen many of these type of hints. I think that it is a bit, you see, you have to combine very many different data sets, which are all have strong degeneracies. and they have larger error bars. In combination, they give you a smaller error bar, which, if all these errors were statistical, there would be no problem. If there's some small systematics hiding somewhere, which was undetected because you didn't look for it, it was tiny, it can pull you a bit from maybe the true best fit. And if you look at these contours, you will see that the cosmological constant sits along the line of degeneracy direction. So usually when this is the case, it means that a small systematic error in one of these data can pull you, or some fluctuation can pull you along the degeneracy contour. So at the moment, I wouldn't say that these results are statistically super significant. But I think that the message that I wanted to convey, I don't know if I managed that, just in a couple of years from now, we will know for sure. So I'm much more excited about the future than the current state.
More questions?
Can I say something to complement what you said? First of all, there is another important anniversary this year, 84, Green and Schwartz anomaly cancellation. That was really the beginning of a string theory we're discussing today. So that's 4 years, right? So that's another important. And I was there. I was in Princeton in 84. David, of course, was there. Kumrun was there. That's when string theory, the way we know it, started being developed. And I started doing that. And addressing the issue of what string theory is good for when it comes to phenomenology, this is the way I got into phenomenology, because I started using it to calculate gluon amplitudes and so forth and so on, which gave rise to yet another revolution that has impact on what we do. So I fully support your idea that string theory is a framework, and now not just a BSM framework, but a framework in general to analyze and describe a whole collection of phenomena about nature, calculational tools, etc., which is unique. The connection with mathematics, hydrodynamics, you name it, everything goes into it. Heavy ion physics, for instance. To me, that is certainly the largest value that's been given, and I see it as being extremely concrete. And it's not vague. I mean, it really, and even if it just stays at that level, even if we're not converging to, finally, a new standard model driven by string phenomenology, I think that the contribution given to progress by string theory is immense, right?
Thank you. More comments or questions? Fernando?
Well, several comments, but since we are all hungry, probably I will be brief and just concentrate on the last point that you mentioned, number 6. I think it's good to have all these observations that eventually people in accelerators are searching for actions and so on. But there is something that people have not dedicated that much, which I'm very excited, which is gravitational waves of higher frequency. So that is good for string theory, but because essentially we have explored from kilohertz down. Oh, good, thank you. From kilohertz down, and we have great expectations, of course, from Lisa and so on. But from kilohertz up, everything is totally open. There are no astrophysics candidates, so anything that can be discovered there will be mostly essentially cosmological and higher energies. So you can go to energies as high as the God scale by exploring gravitational waves of at the gigahertz. So that's something that I think is fascinating, and eventually can help us to test anything beyond the standard model, but in particular, eventually something stringy, with something that we wouldn't have even dreamed by doing colliders, and then the gravitational waves of high frequency can give you something. The problem there is the precision. And of course, there are very few people that have thought about that, because mostly have concentrated on the big experiments. Usually, the higher the frequency, the smaller the experiments. So in that sense, you can even think about tabletop experiments. But there's a small community already that we have had 3 workshops, one in Trieste, one in Cambridge, and the last one here a few months ago. And there's a community building up. think I happen to be the only string theorist at the moment. So in that sense, I would like to just to make the point that maybe other people can get interested.
Yeah, good point. Thank you. Yeah.
It's just like follow up on that. So how do you measure gigahertz gravitational waves in principle? What kind of detector can do that?
Well, there's several proposals. There's action searches somehow. There's levitating sensors. There's electronics with squids and things. People are becoming creative. And the good thing is there are a good community, and some of them based here in the region, and they're taking leadership, and it's a lot of enthusiasm. There's a white paper we have with all the proposals 4 years ago. It's one of these living reviews. And so now we are working on the second edition because many things have been happening in the last 3 or 4 years.
David?
Yeah, I have one question for Marco and related to the questions of Thomas. So what are the prospects, observational prospects about the reheating phase, or more generally the patching between inflation and more recent universe? Because there, I think there are quite some string theory models which try to say things. And is there any hope to test anything there?
Well, usually we would say that the reheating, wherever it is, after reheating, the universe goes through the usual thermal history, which means that you erase all information other than maybe if something that survives. If you can produce some type of particles that are reheating, which then you are sure that they're stable and survive until today, you can say something. The reheating also happens on spatial scales for fluctuations which are much shorter than anything we can observe in reality, so we cannot say much from fluctuations. One way to say something, of course, is through gravitational waves. If there are some sufficiently violent processes that are reheating, they will generate inevitably some stochastic gravitational wave backgrounds, and then depending on the energy scale and like the details of these processes, you may see something like this in gravitational wave detectors. But it is very hard unless something survives. As I was saying, one of the key ingredients always is to have some relic of some type. It's either gravitational waves or some particles or fluctuations, but those fluctuations are very short wavelengths, so we cannot measure them. So I think that the only hope is some gravitational waves, but this will take some time before we get there.
There's a question there.
Yeah, I just want to add to point 6. I already mentioned this in a more informal setting yesterday, but confining gauge theory kind of gives you a way of observing strings. And for example, in lattice gauge theory work, people have access to pretty detailed energy spectra of long-wound strings, completely non-supersymmetric. Hopefully we'll hear more talks about this tomorrow, but that's a totally different window in string theory.
But not string theory as quantum gravity.
Why not? I mean, we all know it's all connected, right? There is gauge gravity duality.
Right.
No, it's just like much less understood, but at least the long string sector is very precisely explored these days and described by Nambu-Goto action to high precision. So why is that not string theory? It does have spin 2 particle, spin 2 blue balls.
Right.
To be continued.
Good point. Thank you. Yeah, here.
Still also on point 6, I think one of the most typical things of string theory is the potential existence of light particles, and therefore modification of the of forces, as Qumran was emphasized also last week. And also the fact, again reminded to us by Qumran, that coupling constants are actually fields, and potentially they may depend on time and space. And so I think in your list of targets for observing string theory, this low energy kind of precision test really very important.
Yeah.
We could have discovered that alpha depends on time. We didn't, but that would have been a nice
We have bounds.
smoking gun.
Yeah. Yeah. Agreed. Ivana?
Yeah, so on point 4, actually, the correct paradigm. So I think a lesson from the Swamp Pump program is that EFTs coupled to gravity in the bulk are extremely constrained, right? But on the other hand, since you mentioned the dark bubble scenario, in that case, there's sort of it realizes some sort of induced gravity, right? Which looks like Einstein at large distances, but it's not a EFT, right? So my question is, how much do we care for phenomenology that the paradigm be to reach actual 4D EFT with gravity rather than something more exotic that does the job for observations, such as the dark bubble?
Well, the universe seems to be described by an effective field theory, standard model coupled to classical gravity, and it seems to work to a large extent. So
yeah, but I mean, to the extent that the observations match the models, the dark bubble somehow seems to still do the job, right? Even though it's not an EFT in that sense.
Right. No, I can only sympathize, but I have no answer. Yeah. More questions, or people want to? Yeah, Ira.
Just one comment to second, like the first thing. Like, I feel that, I mean, we always say that gravity can break the notion of scale separation with the UV and the IR, and that's an opportunity, but it's something which is very hard, no? Like, to make very concrete. And I always feel, I mean, I'm sure that this is something that, I mean, you have all thought since the beginning of string theory, but I feel that if we were able to think harder, what is this UV-IR mixing, like whether we can give something new regarding all the naturalness issues and so on, like whether the decoupling story works differently with gravity and give a new idea for the hierarchy problem, for the cosmological constant, and so on. I feel that this would be like the, I don't know, a major breakthrough, no? I mean, of course, very hard, I don't have any idea, but it seems to me that, I don't know, that's something that we can really give new from string theory to particle physics and cosmology, that there is a chance.
Well, one such an example is if there is a weakly coupled light-dark sector, that gives you a different point of view on decoupling. There is actually not so much of decoupling. The question is, how strongly do we believe this, right? Yeah. Yeah, I think, yeah. Kumar?
I think we can thank our speakers and discussants.